Today we're going to be studying the first derivative test. Now, before we actually look at the first derivative test, there's a couple things we want to review that we've already had in the last couple lessons that will be helpful to remember. First thing I want to remind you guys about is that what we mean by a critical point. So a critical point, if you remember, is basically any value where the first derivative of that value will equal 0, or the first derivative of that particular value does not exist. Or another way of thinking about it, it might be sometimes be referred to it as undefined. So either of those conditions, either if it's undefined, doesn't exist, same thing, or if it's the first derivative at that value equals 0, it's going to be called a critical point for that function. Now, basically, most of the time when we're looking at the first derivative test, we're going to be looking at situations where the first derivative, critical points where the first derivative equals 0. However, there are going to be a couple instances where we'll look at one or two where it's because it does not exist. Okay, now another thing I want to go over is, just review real quickly, is this idea that we had that when you're talking about the first derivative, whenever you have a interval where the first derivative is going to be greater than 0 or positive, that is going to tell us that we know that the function over that interval is increasing or getting larger. And we also know that if the first derivative over a certain interval is less than 0 or negative, that's going to be an interval over which the function is going to be decreasing or getting smaller. And remember, you should be able to kind of understand this because, remember, the first derivative of a function is telling us what is the rate of change of the function. So it's telling us over the interval, as we move along the interval, how is the function changing, its rate of change. And if it's increasing, that rate of change, or the first derivative, will be positive. However, if the function is decreasing over an interval, that means that the rate of change, or the first derivative, will be negative. And the last thing I wanted to go over is an important thing to remember, is that whenever you have a local min point, a local minimum point, or a local maximum point, that's going to mean, remember, those will only occur at critical points. So you know if you have a local min or a local max, it's going to occur when we have a critical point. Either it could be one that's undefined or a critical point that equals 0. Now, remember, don't get that confused sometimes with the converse of that statement. The converse of that statement doesn't have to be true, right? So, remember, if you have a critical point, very often it will be a local max or a local min, but not necessarily, right? But we do know if you have a local min or a local max point, that will occur only when there is a critical point, okay? Okay, so now we're going to look at the first derivative test. Now, the first derivative test is a method or a procedure for when you have a function finding where the local max and local min points will be. Now, sometimes, you might have functions where there's neither a local maximum or a local minimum. Sometimes you might have one, sometimes you might have the other, or both. It just can depend on the function. All right, now the way it works is like this. The first thing you want to do is you want to identify for the function, you want to find all the critical points. Now, the critical points, these will be the x values where I guess you could say they're candidates for being either a local max or a local min, but not necessarily either of them. So you're going to find your critical points. Now, let's say you have a critical point C. Now, what you want to do is you want to find the first derivative of the function. So now we're going to be using the first derivative for the function. And what you do is you want to look to see what happens to the first derivative when it passes over from being less than the critical value C to being greater than the critical value C. And when I say what happens to it as it passes from less to greater than the critical value C, we want to notice what happens to its sign. In other words, does it stay positive? Does it stay negative? Does it change from positive to negative, or does it change from negative to positive? And if you look what we have here, that what the first derivative test tells you, this is going to tell you if it's going to be a local max or a local min. So notice when you go from a little less to a little more than the critical value, the first derivative goes from being positive to negative. That means at C, that critical value, f of C, in other words, in the original function, the value of that function at C, we refer to as a local maximum. Okay, so in that region of the function, that value will be the maximum value. That's why it's called a local maximum. And the other way around is when you're at the value C, which is the critical value, if a little less, the first derivative is negative, and then as you go to being more than C, it becomes positive. That means, the first derivative, that means at C, at that critical value, the value of the function, f of C, whatever the function equals at C, that value will be what we call a local minimum. In other words, again, it'll be in that region of the function that we're looking at. It will be the lowest output value, or the minimum output value. Now, of course, there's also the possibility that when you transition from being a little less than the critical value to a little more than the critical value, that the first derivative does not change sign. In other words, it might stay positive, or it might stay negative. If that's the case, that means that this critical value C that we're examining is neither a local max or a local min. So in that situation, it's neither. So it doesn't always have to be one or the other. Next, I'd like to give you a little sort of like a graphic, intuitive understanding of why the first derivative test works. Now, for example, if you look at the diagram on the left, or the graph on the left, where we see you have a local minimum, if you notice, we know when you have a local minimum, the slope of the tangent line is going to be 0. And if you recall, remember the slope of the tangent line is the first derivative, whatever the first derivative equals. So we know when you have a local minimum, and this would also apply to the local maximum, the slope of the tangent line, it's going to be a horizontal line, it's going to be 0. So we see this is where, as the first derivative test speaks of, we will have a critical value c. But again, we don't know for sure, since they're both going to have a slope of 0, both the local maximum and the local minimum, we don't know if it's going to be for sure a maximum or a minimum or neither. But again, the way we can tell for sure is if we notice when we have a local minimum, you'll notice as you're coming from the left and coming with x values a little less than c towards c, getting closer and closer to c, we notice that the function itself is decreasing, right? F of x is decreasing, getting smaller, right? Lower. But of course, when f of x is decreasing, again, the values for f of x themselves, they may be positive or negative, or we don't know. It might be both positive and negative as you're decreasing. But the important thing is they are decreasing as they come down towards, as the x value is getting larger, it's getting closer and closer to c coming from the left, f of x is decreasing. So since f of x is decreasing, the first derivative is going to be negative, right? Because it's measuring the rate of change of f of x. So if f of x is decreasing as we're coming towards c on the x-axis from the left, the first derivative will be negative. But then as soon as we get past c, the critical value, now the function is starting to go uphill, which means the values of f of x are increasing or getting larger. And again, the actual values themselves might be positive or negative for f of x, but they're increasing, they're getting larger. And since they're getting larger or increasing, f of x, the first derivative of f of x, which is measuring the rate of change, since f of x is increasing, the first derivative is going to be positive. So that's why as we move from left to right of the candidate point, the critical point where f of c equals 0, if the first derivative transitions from negative to positive, that sort of depicts the scenario where we have a local minimum. And of course, everything I just said, when you look at the example on the right, where we have a local maximum, is just the opposite. The first derivative will transition from being positive to, when you're past c, the critical value, to being negative. Okay, so next what I want to do is let's kind of take a look now at a specific example of a function and see if we can find the, where we're going to have maximum and minimum points using the first derivative test. Now in this example, I'm going to kind of specifically, as we do it, this is a good idea for you to pay attention to, particularly when you first start doing problems that are new with a new idea, particularly if you're having a little trouble working them through, is paying attention to these steps. And instead of trying to just figure everything out all at once, what to do, just take it literally one step at a time. Okay, so the first thing we want to do here, it says find the coordinates of the local min and max points for the following function. And then when we're all done, it's nice, you'll see we also like to verify, see the results with the graphing utility. Sometimes it's the old expression, seeing is believing. It's always good to kind of verify it, graphing it, and you can kind of helps you just get a little better feel for what's going on. So here's our function. We have f of x equals x cubed minus 3x squared minus 24x plus 32. All right, so the first thing we want to do is let's find the first derivative. So the first derivative, we differentiate the function, and we have 3x squared minus 6x minus 24. That's step one. Find the first derivative. All right, now what we want to do is we want to find where the critical points are. So again, we're looking for values that are going to make the first derivative equal 0, or where we're going to have a situation where the first derivative is undefined or doesn't exist. So, we're going to take that function, and how you solve it for 0 depends on the problem. Sometimes you might have to use the quadratic formula if it's a quadratic like this one is. There are different ways, but of course in this one, if you look at it, I think we're going to be able to solve this one by factoring it. So we're just factoring out 3 first, so we'll have 3 times x squared minus 2x minus 8. And then we're just going to factor the x squared minus 2x minus 8. And then we set it, we're going to set it equal to 0. And of course we can see that to make the second factor equal 0, x could equal -2, which means the whole first derivative when we multiply will equal 0, or x can equal 4. So those will be our two critical points. Now remember, what that means now is they will be candidate points for being either a local max or a local min. So now the way you want to do this is you want to do one at a time in a sense. So if you think about it, if you think of these candidate points on the x-axis at -2 and 4, it really divides the the x-axis into 3 intervals. So we want to look at the interval from -infinity all the way up to -2. We want to look at the interval from -2 to 4. And we want to look at the interval from 4 to infinity. Now, again, ultimately what we want to do is see is the first derivative in all of these intervals going to be positive or negative. Now the idea is you can pick any x value you want in an interval to see if that x value comes out to be, when you put it into the first derivative, to see if it comes out to be positive or negative. Because the reason you can pick any test value is because all of the first derivative values between critical points will all be the same sign. So it really doesn't make any difference which value you pick. You might as well sometimes just pick one that's just a little bit easier maybe to do the arithmetic, but you can pick any of them, okay? So again, you can pick any value you want in these intervals between the critical points to test to see if all the first derivative values in that interval will be positive or negative. So I'm picking from -infinity to -2. I'm picking -3. Again, I didn't have to pick -3. I could have picked -10. I could have picked -6.9. Anything I want. It's going to be less than -2. Between -2 and 4, I might as well pick 0. 0 is a nice, easy number. Didn't have to pick 0. Could have picked 1. Could have picked 2.6. Anything I wanted as my representative value for x between -2 and 4. And from 4 to infinity, I'm going to pick lucky 7. So those will be my test values. So now, you can do this on a calculator. You're going to take -3, plug it into the first derivative function, and it comes out to be 21. Now again, the key thing here, remember, is I don't really care that it's 21. What I really am noticing is that it's positive. That's the important thing. It's positive, right? When I put 0 into the first derivative function, that one comes out to be negative 24. But the important thing is it's negative. And in my third interval, when I'm looking for values that are greater than 4, I'm using 7, and I put that into the first derivative, it comes out to be 81 for the output for the first derivative, and again, that's positive. So now we're ready to do our final step, step 4, which is actually to determine whether our critical values, negative 2 and 4, are local maxes or local min points. So easiest way to do this, just make a little number line if you get a little mixed up on this. And you put negative 2 where that is, you put about negative 4 on the number line, negative 2, and then you put positive 4 where that is. And now what we want to do is, if you recall, when we put in negative 3 into the first derivative, it came out to be 21, which is positive. So I'll mark, so you can see that that's a positive, the first derivative is positive in that interval less than negative 2. And between negative 2 and 4, that's where I used 0. When I put 0 into the first derivative, that came out to be negative 24. So that's a negative value. So that means in that entire interval, the first derivative is going to be negative. And then in the third interval, greater than 4, we use 7 as our test value that we put into the first derivative. And that came out to be positive 81. So they're all the first derivative values will be positive there in that interval. So I'm marking that as positive. So now when we look at our critical value negative 2, as we go from left to right, as we pass over negative 2, we see that the first derivative went from positive to negative, and the first derivative test tells us that that means at that critical point, negative 2, we will have a local maximum. And the value will be what we get when we put negative 2 into the original function now, not into the first derivative. Because remember, ultimately, this is a test about the to tell us information about the original function. So now we've determined negative 2 is the critical point where we're going to have, by the first derivative test, a local maximum. So when we put negative 2 into the function, we see we get 60. So 60 will be the local maximum, and of course the coordinates will be negative 2, 60. And of course, when we're looking at 4 now, that is the other candidate critical point. We notice that the first derivative transitions from negative to positive, and again, that means the first derivative test tells us that this is going to be a local minimum. And again, the value of that local minimum will be what we get when we put 4 into the original function that we're talking about, and that comes out to be negative 48. So the coordinates for that point will be 4, negative 48. And then right below that, if you look at the graph that we have of the original function, you can actually see that we do have sort of a little mountain peak or local maximum at negative 2, 60. And we also have a local minimum, or the bottom of a valley in the graph, when we're at a point where the coordinates 4, negative 48. And again, this is for, we're talking about the original function. Okay? This problem is a application problem of the first derivative test to a geometry problem. So if we look at the picture here, what we have is a right triangle, And what we want to do is we have a rectangle which is placed as shown in the diagram. And what we want to do is find, given the dimensions of the right triangle, 3, 4, 5, what should be, if we can sort of change the dimensions of that rectangle by sliding the upper left corner point of the rectangle along the hypotenuse of the triangle. So what the question really basically is what will be the maximum area of the inscribed rectangle that we can come up with. So to do this problem, as is often the case in these word problems, is what you really want to do first is you want to come up with a formula for the area that only uses one variable. And if you look at the problem, we know that area of a rectangle is length times width, which is 2 variables. So a way we can do this is to recall a high school geometry theorem, which was that when you have a triangle, it doesn't have to be a right triangle, it can be any triangle, that when you take a line and you draw it cutting through the triangle parallel to the base, what will always happen is the top triangle you form will be similar to the original big triangle. So in this case, what we can say is that the base of the top triangle, which is L, to the base of the large entire right triangle, which is 3, will equal the right side of the right triangle of the small upper right triangle, which is 4. The right side of the small upper right triangle, which is 4 minus W, to the right side of the entire big right triangle, which is 4, right? So it's like the ratio of the corresponding bases will equal the ratio of the corresponding right sides, right? So now, if we want to solve for L, we can just cross multiply and we'll get 4L is going to equal 3 times 4 minus W, which will be 12 minus 3W. And then we can solve for L just by dividing by 4. So we'll have L equals 3 minus 3/4 W. So now the area formula is W times length, but for length we can substitute in 3 minus 3/4 W. So now, just using the distributive property, multiplying W times what's in parentheses, we have our A, or area formula, in terms of W, or function. So A of W, the area in terms of W in the rectangle, the area of the rectangle is going to be 3W minus 3/4 W squared. And now we have the area formula for the rectangle in terms of just one variable, W. So now we're ready to employ the first derivative test. So we take the first derivative. We want to see, ultimately what's going to be the maximum value for this area. So we take the first derivative of the A function, and we get 3 minus 3W, 3 minus 3/2 W. We set it equal to 0, and we solve to see what value for W makes the first derivative equal 0. And we see that we get W equals 2, so that will be our critical point. So now what we want to do is, we know that our critical value is 2, and we want to see what happens to the first derivative sign as we transition from to the left of 2 for W values less than 2 to greater than 2. So if you take any W value you want less than 2 and you plug it into the first derivative, you'll see that the result will always come out to be positive. So that means when the first derivative is less than 2, we're getting out positive values, and it's positive. And when you try any value you want for w greater than 2 and try that, any value greater than 2 in the first derivative, you'll see that that result or output is always negative. So that means all first derivative values greater than 2 for w will be negative. So the first derivative test tells us, since we're going to transition for the first derivative going from positive to negative, that means that at the critical value of 2, we will have a local maximum. And to see what that maximum value is, we plug 2 into the original area function that we have, and we see we get an output of 3. So that means that will be the maximum area for the inscribed rectangle, 3 square units. And it's going to occur when the length of w is 2. And we can sort of, again, it's nice to graph our result, and we can see from the graph that indeed the local maximum does occur when the width is 2, and the area formula shows there that this local maximum is going to be 3. You'll also notice that this happens sometimes in word problems. We have to restrict our domain for our inputs for w from greater than 0 to from 0 to 4, but not including 0 and 4, because if you look at the the nature of the diagram here, the width of the rectangle, the way we have it set up in our diagram, cannot be has to be less than 4 in the triangle, and it also has to be greater than 0. So that's why we're only showing that part of the graph. This is an example from algebra where we can use the first derivative test. So in this problem, we're looking for two positive numbers, x and y. We want their product to equal 800, but what we're trying to do is find two such numbers such that the sum of x plus 2y is as small as possible. So in this problem, just like in the previous one we looked at, what we really want to try to do is get a formula or a function for the sum in terms of one variable. So since we know xy equals 800, we can say that y is going to equal 800 over x, and therefore the sum x plus 2y, substituting in for y, 800 over x, we can get that the sum equals x plus 1600 over x. And now we have the formula for the sum that we want to minimize in terms of one variable. So now again we're going to find the critical value, so we're going to get the first derivative, and that will equal 1 minus 1600 over x squared. We'll set it equal to 0. Keep in mind that for this problem the domain of the function is going to be that x has to be greater than 0 because we want the numbers that the problem says to be positive. So solving for x, we get that x equals 40, so that will be our critical value. Now, if you plug in any value less than 40 in for x, you'll notice that the first derivative is going to come out to be negative. And when you try any value you want for x greater than 40, the first derivative is going to come out to be positive. So according to the first derivative test, that tells us since at the critical value, the first derivative of the critical value of x equals 40, the first derivative transitions from going from negative to positive. That tells us that at 40, the critical value of 40, we are going to have a local minimum, and the local minimum will be what we get when we put 40 into the function for the area for the sum of the x plus 2y, which we're using in terms of the one variable x, which comes out to be 80, and that will be the local minimum. Now, and that will be the minimum value for their sum. So what we're going to have is the values for the numbers should be x is 40. And of course, since xy equals 800, that means y, the other value, will equal 20. And again, it's always nice to look at these graphically for verification. So when we look at the graph for x greater than 0 of our sum function, we can see that we do indeed have we do get that minimum value when x is 40, and the coordinates of that point is 40 comma 80, when the 80 represents the sum of x plus 2y. And again, also notice in this graph, so there's no confusion that you might have about this, that the y-axis doesn't represent the y in terms of the number y, which came out to be 20. Remember, the y-axis here is representing the sum of x plus 2y, which is written in terms of x, which is, the x plus 1600 over x. That's what the y-axis is representing here. No discussion of the first derivative test would be complete without looking at two special cases. Now, the first case we want to look at here is a situation where we're going to have a undefined first derivative, or a first derivative that doesn't exist, and see what happens here. So let's look at this example, take a simple example where we have the function f of x equals the absolute value of x, and we're looking to find local minimum or maximum, or neither. So, or both. See what happens. So if you think of the function, the absolute value function, when x is greater than 0, the first derivative is going to equal 1. But when x is less than 0, the first derivative is going to equal, for all values less than 0, the first derivative is going to equal negative 1. So therefore, if you remember that in order for the first derivative to exist, the limit from the left and the right has to be equal. So in this situation, the first derivative at 0 is going to be undefined. And therefore, at x equals 0, we will have a critical point. So at x equals 0, we want to now see what's going to happen to the first derivative as we move from the left to the right, or from less than 0 to greater than 0. And we know that the first derivative to the left is negative 1, so it's negative, and to the right of 0, it's positive 1, so it's positive. So therefore, this is a situation where at the critical point, the first derivative changes from negative to positive, which means at the critical value or critical point of x equals 0, we're going to have a local minimum, and that local minimum will be f of 0, and the absolute value of 0 is 0. And again, you can see this represented in the diagram, the graph diagram, showing you where f first derivative is negative, transitioning to positive, and again, at 0, the first derivative, this is an example where it doesn't exist, but it's still going to be, using the first derivative test, a local minimum. This is an example where it's another special case example where we're trying to use the first derivative test to see where we're going to have possible local local max or min values or points. So what we're going to do is let's look at the function, for example here, f of x equals x cubed. So the first derivative is going to be 3x squared for the first derivative. To see any critical values, we'll set it equal to 0, 3x squared, and we see that x equals 0 will be a critical point. Now, when you look at values, all values to the that are less than 0, you're going to see that the first derivative is always going to be positive, because you're always going to be doing 3 times squaring a negative number. It's always going to be positive. And also, when you do all values that are greater than 0, you're again always going to be doing 3 times squaring a positive number. So again, first derivative is always going to be positive. So this is a situation where we're at the critical value, where the critical point x equals 0. The first derivative, as you transition from less than 0 to greater than 0, the first derivative does not change sign. In this case, it stays positive. So that means that there is not a critical, at this critical value, it means there is not going to be a local max or a local min. So this function will not have any local max or local min. It does have a critical point, but in this case, since there's no change of sign of the first derivative, it's not going to be a local max or a local min. And again, when you look at the curve, you can see that it doesn't represent sort of a peak or a valley in the function, right? So it kind of all makes sense.